Okay. Welcome to STEAM Cafe for September. My name is Angela Metler. I work in the President's Office at South Dakota Mines. We've been doing STEAM Cafe since April of 2018. And we want to thank everybody who has joined us in person and virtually for letting us continually do this successfully. STEAM Cafe is a partnership between South Dakota Mines, South Dakota Public Broadcasting, and Hay Camp. So we want to thank them as well. Before we really get started, the STEAM Club is here tonight, and they are selling pizza at $3 a slice as a fundraiser for their club. So those of you who are lucky enough to be here in person, you can take advantage of the pizza. So tonight's presentation is entitled Materials, Spinal Discs to 3D Printed Objects, presented by Dr. Katrina Donovan, who is a lecturer in materials and metallurgical engineering at South Dakota Mines. I will let her take over.
Thank you, Angela. Good evening, everyone. Thank you for having me. As Angela said, the title of my talk is Materials, Spinal Discs to 3D Printed Objects. Diving right in, I always like to know who's presenting. So just a little background on me. I was born in South Dakota, grew up in Bennett County, graduated from there. I'm also an alum of School of Mines, so it was very fun to be able to come back. After I graduated from School of Mines, I moved to the San Francisco Bay Area, worked there, and I also got my master's. From there, I moved to Oregon State University, which is just a little south of Portland, just to give you a little bit of area. While I was there, I got my PhD. I also had the opportunity to work at HP, and I'll be talking a little bit about the stuff I did really while I was in Corvallis, Oregon. And then when the opportunity came to come back, I was really excited, and I was able to take a faculty position at School of Mines. So I'm very excited to be here this evening. Quick outline of kind of where we're going. I'm giving what we like to call case studies. So two different case studies about what I'll be talking about tonight. First is the spinal disc, and the second is 3D printing. And these both have similar themes running underneath them, but I'll give you background in both, and then kind of a design approach for 3D printing and more of a results from the spinal disc. From these two case studies, I'll then talk about how, as a faculty member and a teacher, I'm able to integrate what I've learned and done on a high level in terms of research, and how I've integrated that into the curriculum, and not just the curriculum at a college level, but also at an elementary, pre-K, and high school level. So kind of the whole gamut. And from there, I'm going to talk about just current and future work that I'm doing, from STEAM outreach to the clubs I'm involved in, and then just wrap it up with a conclusion. So getting started. So spinal discs, you're looking at these and you're saying these aren't spinal discs. Those are. These are not spinal discs, these are gel beads. So really, I got into spinal disc research in a really interesting way. I was between my master's and my PhD. I was writing my dissertation, and I have two children. And I had a friend, and he goes, hey, come to this, science activity. I'm like, I have two kids right now. I'm like, I'm not sure how well those would mesh together. And he's like, no, come, it'll be great. And what we got to do is actually this right here, which is gel beads. And what gels are, I'll give you a little description about that. But let's talk about polymers first. So polymers are described as a long chain molecule with thousands of repeat units. Well, what does that really mean? So if we break down the word polymer, poly means many, mer means parts. So if we think of a mermaid, it's part made. So polymer, many parts. So if we start with a single paper clip, this would be our mer. As we start adding on to these paper clips, we start getting these really long chains, right? So this is a polymer chain, if you will, imagine with me. So a long chain of repeat units. What we had in this activity was sodium alginate. You guys have probably eaten sodium alginate. It comes from kelp. It's a thickener in a lot of different foods, from the shakes that you eat to dressings. You can see it in a lot of different places. I said you've probably eaten it. Well, the fun thing is this is an activity they do with kids. They're actually cross-linking it. And what we mean by cross-linking is you have these big chains. And when you put the sodium alginate in a calcium chloride solution, they start tangling. You can see my chains start getting longer and longer as they start cross-linking. So it makes these big polymeric networks. When you start getting really big polymeric networks, you actually get into where they're tying together, and you actually form these gels. So you can think of things like gelatin. And that's really what these are here. These gel beads are actually 98% water, so they're what's called a hydrogel. So I really had a lot of fun with this activity, was really interested in the science behind it. And so the person running the activity, I spoke with them, and they're like, hey, I have a project you might be interested in. And that's how I got into spinal disc research. So with spinal discs, it's a problem that many people see across the world, or across the US specifically. We have about 75% of our population that either has a herniated disc, a bulging disc, there's some sort of back pain that they have. So the current treatment for this is reduced function, it reduces the functionality. So we're fusing your spine, we're removing part of it and put something in. So there's a lot of just reduced functionality. It's not bending like we're supposed to, twisting. It's all a very reduced motion. Specifically, I'm going to talk about herniation here. And what we have with herniation is we kind of have two parts to our spinal disc that we're going to focus on. We have the nucleus pulsus, and it's described as a jelly-like substance. So back to that gelatin. The outer part is your annulus fibrosus. It's much more rigid. It holds all that gel together. But really, your spinal disc acts as a shock absorber. So if you imagine jumping, it's your spine helping absorb that shock. Twisting, turning, you think about somebody like a truck driver, they're driving and every day they get that bouncing. It's those spinal discs absorbing all those shocks. Not all, it's other places as well, but a good chunk of it ends up here. And that's why we see things like this, with this herniation where you see the jelly actually slipping out, not the jelly, the nucleus pulsus, that jelly-like substance slipping out. So what we have here is compression on the spinal nerve. It induces severe back pain. There's a lot of problems with this. So for this, I'm going to approach this from two different ways. The first way is we're going to look for a model, and you're like, well, why don't you just use humans? Well, I asked humans. Nobody wanted me to go in and take out their spinal disc, a nice healthy one, and test it, because that kind of reduced, the whole point of this, right? So I had no human donators. But the nice thing was there was a study that was done on humans. They were in car accidents. It was post-mortem, but they said what they found or had suggested was bovine discs would be a really good option. And so that was one path we took, is we need a model. We need to know what, if we're going to synthesize these gels, what do we need to compare it to? So here we have a dissected bovine disc. You can see we've punched out the center because this is the annulus fibrosus on the outside. Inside we got the nucleus pulsus. So we punched those out, and what we did was we did mechanical testing on this. So really what it is you have your disc, and we're just making little pushes down on it. You guys have probably been walking through a store and you see the chair and there's that foot punching into the chair to prove the life of the chair, right? The cushion. So similar kind of concept here is we're just trying to get mechanical properties in terms of compression out from this. So that's what we were doing here, and we wanted to do it in two different states where that annulus fibrosus was around it and supporting it, and then also just it by itself. So that was the first approach. The second approach is, all right, if we do get this model, and we want to synthesize disc, like how are we going to get it in, right? So if you have your disc herniating, the thought process we had was like a tire. What happens when the air goes out of your tire? Pump it back up. That's what we do. We'd essentially insert a liquid gel. It would cool a liquid, and it would cool into a gel while in there. So that was the second part. So that's when we started looking at hydrogels and composites. And so kind of not the exact same as the sodium alginate. We used agarose, which is also used a lot in food, but a gel nonetheless. We have a high water content, so it's biocompatible, works well with the body. Similar thing here, we made it about the same size as the discs were about 8 millimeters. Then we tested them. This is just kind of a fun picture of the geometry we used. You can see this one, the gel was kind of sticky and stuck to the top. So the two approaches we're going. So with these, for the spinal disc model, you can see on the left-hand side, what we did was this compressive modulus. So back to that squishing, and we look at this data, you kind of get two different sets of data here. You get what's called a storage modulus, and that just tells us how elastic the response is. So elasticity being, we stretch a rubber band. You have one in my pocket, you stretch it, it'll snap back. We're kind of getting information about the viscoelasticity. The big thing to note from this is I have all these trials. We dissected a lot of bovine discs. And you can see that data here. The big thing is we overlaid the human data that was reported, and we found it was a pretty good match, which was pretty exciting. On this one, so this was the bovine disc. The next thing we did is we went and looked at a couple different hydrogels. And when I say composites, one of the things we did is we added things to the gel. So what does that mean? Well, if you guys have ever made Jello at home, what do we sometimes put in Jello? We put in fruit, right? So we have a Jello with the fruit in it. You put in nuts, sometimes you get these Jellos with a lot of different things. That's kind of what we're doing here. Instead of fruit in our Jello, we're putting in more rigid structures to help with that shock absorption. So the one big thing to note here that was a little bit of a bummer for us, we need to go back to the drawing board, is we're sitting here between 10 and 100. And here we're sitting between 100 and 1,000. So we actually made our gels too strong. So we had to go back and work on this, but it was a good first try because we were doing both of these at the same time. So kind of two different ways, but we needed to go back to the drawing board. We did some other tests on these, an unconfined compression. The other one I wanted to talk about is we also did shear. So what is shear? So if you're turning, I would kind of be a shear motion. So we did some compression and then some shear testing. So that's what we got from this. Kind of a quick wrap up from this. The cool thing was we did find a pretty good model with the bovine disc, like we had said. I got to work with 7 different undergraduates on this project, 1 high school student, and one of the cool things that actually came out of this is we spent a lot of time with synthesizing the gels. That somebody else saw this and they were like, what if you put nutrients in it? So we actually had a spin-off project where we were actually treating burns and stuff with hydrogels. So kind of cool, just the different directions it went. And then one of the big things I like to talk about is we got to present this work a lot, and then here's a lot of the group members I worked with on that. So that was kind of one little project. So that wraps up our first case study. Second one, we're going to go into 3D printing. And for this talk, I'm going to focus mostly just on polymers. I have also done some work with metals. There's a lot of cool metals out there, but I'm going to stick with polymers. Lots of different examples here. This one's pretty cool. When I was at HP, we were working on that, and they 3D printed a link. It was then a link in a chain. It can hold over 10,000 pounds. So there's a pretty fun YouTube video with that. It's pretty crazy to watch. And then just some other fun things that we did. To get into 3D printing, though, I kind of want to talk about just manufacturing in general, because I don't think there's a good understanding of what 3D printing really is. So let's start with formative manufacturing. This is something most of us probably see. So in this one, you start with a form, you put in your material, then you come out with something. So we see this injection molding, stamping, casting. Anybody who has a glass in here, you know, some sort of mold was used for this. So what it is you have mold you put into it. So that's one type, that's called formative. Next type is subtractive. So somebody who works with a block of wood or maybe a block of metal, you start with this part here. So you start with your square, you do CNC, turning, drilling. There's a lot of different things you can do. The big thing to note though is look at the design. At the end of the day, we're still getting the same thing, right? Last one is additive manufacturing. Additive manufacturing, specifically I'm referring to 3D printing. What it's really good for is prototyping. This is what we're going to be talking about. So prototyping, let's say I want one of something, I'm not quite sure if that's the size I want. So you can print it and say, ooh, that's too big, that's too small, and go back to the drawing board. Sometimes for these processes, it's a lot more expensive to do. A mold can run you upwards of tens to hundreds of thousands of dollars. So if you don't get the geometry right the first time, you're kind of in a bad spot, right? But this is great for high volume. The plastic water bottles we drink out of, injection molded. You know, simple geometries, this works well, but this is pretty fun because it can be customizable to everyone, to the shoe, to your hand. So really fun for 3D printing, and that's where we're going to be today. So talking a little bit, how do we 3D print, you know? Well, first you need an idea, right? We got to start with an idea. You can start with something as simple as a picture, a drawing, and then you go to what's called computer-aided design. And this doesn't even begin to cover all the different types of computer-aided design. In the research realm, I use Fusion 360 a lot, but Tinkercad's actually probably my favorite because it interfaces really nicely with the young age. So if you have something, it's quite nice to build in here. So once you've built your object, you have your idea, you've now built it in your CAD software, what do you do next? You actually put it in what's called a slicer. So if you imagine a book, you know, we have many, many different layers right there. We have a page. That's essentially what this is doing. Imagine it's slicing. It's making pages in a book. And that's what this does, is it slices it down. So like we saw on this slide, imagine those slices. It's exactly what it's doing here. And then we get to the 3D printing part. So kind of the 4 steps to 3D printing right there. When I was at HP, a lot of the thought process we had was a design approach, and we teach design and engineering. But fit, form, and function are the 3 things we really focused on. And what we mean by that, fit, as it describes here, refers to the ability of the part or feature to connect, mate with, or join with another feature or part within an assembly. So maybe we have that link in a chain and we need to 3D print one more. So that would need to fit in there. Form refers to such thing as characteristics, such as external dimensions, weight, size, visual appearance of assembly. So some things, you know, if you need a bolt that goes under the hood of your car, we probably don't care what that looks like, right? We just need it to function properly and we need it to fit. you know, the way it looks, if it isn't pretty, that's okay, we're not gonna see it. Form is really where that visual appearance might become quite important. And last is function. This is a criteria that is met when the part performs its stated purpose effectively and reliably. So those are kind of the 3 big things when we're 3D printing for an engineering we're kind of shooting for. This is what I like to 3D print for. So I'm in the fun everyday life sort of thing. I would like to add it's functional. This is probably actually one of my favorite things we 3D printed. I 3D printed a lot at HP, but this one was fun. We actually had fruit flies that were really bad that summer. And so what this does is it has big holes that go down to small holes, so the fruit flies get stuck in there. They're not hovering around your bananas. So yes, I was building a lot of cool things, but what I think is the most amazing thing about 3D printing is there's something in your everyday life that's annoying, like a fruit fly. You know, this can actually be a problem solver, and it can be a problem solver in your home and everyday life. And I love that about 3D printing. This is another thing I did at HP. Not my favorite picture, but what we did is we actually did scans of people. So we did 3D scans, and then we printed them, which was super fun. We also did that at 3D printing camp in the summer. So just a lot of things I like to, you know, emphasize is, sure, there's a lot of engineering, amazing things we can do with 3D printing. I'm happy to have been a part of that, but there's so much fun, useful things that, you know, might not kind of think of that 3D printing is really great for. So having it in your home is an awesome thing. So that kind of finishes up our segment on the case 2 3D printing study. Next thing I really want to talk about is STEAM curriculum integration. I'm using both of these as examples. And this is just a bunch of pictures of a lot of different STEM outreach I did. Some of it's in the classroom, but really it was just a transition slide. So the first thing that I wanted to talk about was I teach a class at School of Mines called Properties and Materials, and this is a lab class. And when COVID hit, a lab class, especially at School of Mines, we're really hands-on. We like to get our hands dirty. I like to get my hands dirty. You know, going completely online was a really big challenge for us, and some of the feedback I got from my students was just the complete lack of being able to get their hands dirty. So we kind of had to look for creative opportunities here. So in class, this lecture ties a lot with the class, and what we were learning was phase diagrams. And I know I'm not gonna get too sciencey on you, but here we have a temperature on the y-axis, and then on the x-axis we have essentially composition or concentration. So the thing we wanted to motivate here from this lecture of the class and then into lab was how if we know temperature and concentration, we can determine whether we're in a liquid phase, a liquid and metal phase, or a metal phase. So A, as you can see here, would be in a completely metal phase. B, we're right in that liquid, a 2-phase region with liquid and solid. So that was really the motivation for this first class. So as I said, we all got put home. So what did I do? Well, I went actually back to that case 1 study. Remember we were making Jello? Well, I can do Jello at home. The way Jello works is it's a little different than the gel beads. This actually requires temperature. So gelatin is a polymer. So when it's in cold, it's like this. But if you imagine you heat it up, what happens is those polymer chains start unraveling. And so when they start unraveling, they become long, they can become entangled or interwoven. So if you think about something like spaghetti, right? Spaghetti is a big mess of strings. That's kind of what we have going on here. So when you see it, have them in a hot liquid, your liquid tends to thicken, and that's just due to those polymers unraveling. So other thing that can happen is they align with each other and tangle. And here's what gelatin looks like. So we have temperature, and I talked about in this previous slide, we needed, you know, a temperature. Next thing we want to do was go into concentration as well. So here's kind of just the standard recipe for gelatin, but what I had the students do was modify the amount of gelatin they put in and then the temperature. So don't need to spend too much on this. But the big thing is I wanted to go from what we were seeing in the lab, seeing in the textbooks. We have temperature, composition, we have this liquid region. I wanted to essentially do that, but with the gelatin. So what we have here is one of the students' results, but if we look, we have this region down here, which is liquid, this region, which is a gel and liquid. So we get in that 2-phase region like we saw here, and then this solid region, which represents that. So kind of doing this in reverse. So if we look at what our gel samples look like, and I'm sure this probably doesn't come through as well, but you can see the bubbles. We actually have just liquid, and there's little red dots in there. So that was a really cold sample because we're really low on the temperature and we're really low concentration. So what happened in this example is those polymer chains never unraveled, so we weren't able to really get any gel in those, which is what we'd expect. So just a liquid region here. The next one, it's kind of hard to see, but we actually have a chunk of jello here where it did cross-link and we are entangled and we actually have a solid form. But as you can see down here, we actually have liquid too. So this is what we call a two-phase region. We have both solid, both liquid, like we saw in the phase diagram before. And this last one in the upper right-hand corner, we have all solids. So we have big scoop of jello. This didn't last long at my house. My kids ate it quite quickly. Also the liquid and solid. They were not partial to any region. They liked it all. But I was at least able to get some pictures in before class, which was nice. So that was me saying, hey, here's my images. What I then had the students do is the students, they had to build their own jello. Big thing to note is they were locked at home and I still got some smiles. So I felt like that was a win from the lab. One student, they actually had Easter, so he made a whole thing. One student, this was really cool. It looks like there's nothing in there. He actually used a see-through or a clear gelatin. It didn't have any colors or dyes in it. So overall, it was a lot of fun. The students generally enjoyed it. It was kind of cool to see that transition. This one I really liked because he had his control and then he wanted some really, really rigid jellos. So he said they were quite chewy by the time he was done. I don't want to know how many boxes he used. It was probably a couple, but he said he had a lot of fun, which was good. All right, so that was one example. I teach also structure and properties materials class. So I said I was doing the lab. I actually teach the class too. That term I wasn't. But last fall, one of the fun things we got to do, and I wish I would have had some hand models really, but here's some sliced images of different splints. And so the project here was design a plastic splint for your injured digit that you can print on campus. So the fun thing with this was we actually had students measure their own finger. They had to pick their finger or their digit and then build 3D, or they had to build in CAD, and then we 3D printed a lot of them. It was pretty cool because a lot of students didn't realize little things. Like one student, they were really excited to see theirs, and they didn't realize their units were in millimeters or in inches, and I printed in millimeters. There was, you know, little things along the way that were pretty interesting to see, but there are some students that came out with some really cool things. I kind of mentioned earlier, the cool thing about 3D printing is the customizability, right? One student, he wanted to, I think he wants to be a medical doctor, but what he did is he actually added his name to the top of it. And he goes, wouldn't this be cool to have in a hospital? And then when a kid hurt his finger, you could just have his name on his own splint. And I was like, that's super cool. Should put his up there. But that was one really cool thing that came out of it was that. Another example of 3D printing was in MET 352, which is the Principles of Engineering Design. It's a junior design project, so they have to start with something and do, they have to start with something and then all the way to making an object. So for this one, it was design a ship to be 3D printed that will later be used to create a small mold for casting. So we had to 3D print it all the way to actually casting their own thing. So you go from a polymer all the way to your casting with the metal. This was in the spring of last year, so I don't have any sweet pictures of the casting, unfortunately. But we did get to 3D print them. And once again, it was life on the fly. So one of the fun things we were able to do with it is we were able to test them in the little creek by my house. So I really need to thank all the MET 352 students because they kept me and my children sane, because I don't know how many times we tested these boats. And it was fun because we filled them up with a mast. So they had to hold the mast and then also float. So it was a pretty fun little project. It kind of got morphed, but this spring we'll be actually casting. So I'm pretty excited. So that's just 2 examples of case study number 2. Big things that we learned from this is material selection. A lot of the students hadn't used CAD yet, and for both of these it's 3D printing. The other cool thing about this project was we also got to do process development from all the way to casting. I mean, we didn't this term get there, but the students had to work that part of it as well. So also got process development on that one. All right, once again, another transition slide with lots of pictures, but this is into current and future work that I'm doing right now in terms of STEAM. On the left-hand side, this is blacksmithing. We've got some 3D printing down here. This was a STEM outreach where I was talking about additive manufacturing. So additive being adding, so it works well with Legos because you can add things right up. Another STEM outreach, so transitioning kind of a little bit more into that. One of the big things I really help out a lot with is 3D printing. I kind of enjoy doing that. They actually have a 3D printing camp every summer. They didn't list last summer, but the big thing is it gives the students a lot of opportunity to both create their, create their ideas. We also had some STEM activities involved, like they had to 3D print a bridge, but they couldn't 3D print it all in one. They had to essentially do like a plastic welding. And so we see right here where the student is welding his, plastic welding his bridge together, which is pretty fun. And then we had the students talk about them. So super fun camp. I really enjoy doing this sort of outreach. And we have the winners up here, but it was a great opportunity for those students to get involved with 3D printing. So I'm really excited to talk about this. This is actually a really new club on campus, something I and a couple other people have definitely been spearheading, but one of the points of this club is exploring the artistic side of material science, and 3D printing definitely fits in there. Even the gel beads, one of the things I found with just gels in general, anytime you put colors with kids, you can start talking about color chemistry, which is also interesting. But this club, we're definitely looking at the artistic side of things. And we're looking at things from metal clay, glass bowing, casting, engraving, and just so many different things. Last year was our first full year of going, and I was pretty excited. What we have here is Bismuth Crystals that they grew. They also had an opportunity to do some stained glass, construct those. Another thing they were gonna do was glass blowing. We didn't have the opportunity to. See the stained glass up there. Another thing is they do, there's just a lot of collaboration with the blacksmithing club. They're a club I work with a lot as well, but they do a lot of bladesmithing. You can see my hook up there. I'm definitely not a pro. They teach me every time I go down and blacksmith. But the STEAM club, their big motivation is just to engage with to engage in STEAM activities with the local community. So like they're here tonight selling pizza, but they also spend a lot of time, doing family science and engineering type nights at elementary schools as well. Another activity that I've been really active in is what's called WISE, or the operation. And Dr. Walker and Dr. Morrow were actually spearheading this. I helped a lot with just 3D printing parts, but the WISE group, which is Women in Science and Engineering, they are making a WISE board. And so I helped with 3D printing the different parts. So the really cool thing about this is I've pulled and stretched and made these images much larger. But the cool thing is all these 3D printed parts, they're two size. So when you put the heart in, it's actually the size your heart would be. The femur would be the size the femur is. So pretty cool just kind of seeing different parts of those. The other awesome thing is you can see the detail here in terms of the veins. We have the trachea here. So that was a really fun project to work on, just helping Dr. Morrow and Dr. Walker with that. This is probably the newest project I'm working on and really fits all the way into this theme. This is polymer processing. And so I'm sure we're all aware of just the different problems we have in terms of recyclability of polymers and plastics in the world. What we have here is we actually have a shredder, and it's a bike, and you pedal it and then it'll shred your plastic for you. So the big thing here that we're doing is you can cut up a plastic, like just smaller, cut up the plastic bottle, and then you can put it in there, and the bike as you pedal will shred it for you. So this is a fun activity here. The big thing though that we can do is once we've shredded up this plastic, it's recycling it. So we can go one way here where we put it through what's called an extruder. And the extruder will heat up the plastic, and then it will extrude, or it will come out the end. And you can actually do things like make filament for 3D printing, or you can attach a die to it and you can do other shapes with it. But the kind of what I'm interested in would be from extrusion down to we'd be making our own filament, and it'd be recycled filament. So that's one way, so we can do that. The other aspect is we can go to what's called injection molding. And if we think back to my slide that I had a long time ago where I was showing about 3D printing, and we had the formative one where we had the mold. That's essentially what we have down here, is you would take the plastic from your shredder, you'd then put it into the injection molder that would heat it up, you'd press it down, and it would go into a mold here, like we see. These are aluminum molds. So then you could be making hearts and seafish, or seahorses, starfish. So that's really kind of the process we're working on. We got the shredder, and we're on the way to purchasing the injection molder. So really fun polymer processing we can talk about here. And this is a cool project because it extends from high school student, which we have here, operating the shredder, to we have graduate students working on this project. So pretty fun here. So in conclusion, from using, if you read the abstract for this, I talked about everyday life. So from stones to grinding grains, we talked about wielding swords in battle, and more recently to exploiting polymers to create lightweight materials, from spinal discs to 3D printed objects. We've kind of covered all that gamut here. We've also talked a little bit about materials creation, characterization and production with materials. And we had a couple different examples from really soft materials with those hydrogels and those jellies, all the way to harder materials. So I did give you a couple metal examples. Kind of covered the gamut there. And then really my hope is to have bridged the gap between really complex materials, you know, something like a spinal disc. Hopefully you can understand how that would relate to something like jelly or gelatin. And a lot of the technology we use, like 3D printed technology, how, you know, we can build some amazing things, a link in a chain that can hold a car, but we can also build something as simple as a fruit fly catcher with it. So hopefully bridging that gap between, you know, these really hard concepts, but how we really use so many of these ideas and concepts in everyday life. Then this is one of my last images. I think we have like 3 different things going on here. We have the station set up, and we have students that are doing, I can tell you the name of it. Legos, sorry, Legos for additive manufacturing. We have gel beads over here, and we actually have another station that is, they're doing 3D printing, but it's by hand. So instead of a XY board, they get to do it by hand. So just wanted to give a shout out to a lot of different people that helped, and a lot of different stuff I used, from HP all the way to the Oregon State University, my professors group, and then it was really great that I had so many students and student projects that were willing to let me share their stuff. Special shout out to the STEAM Club and the Blacksmithing Club and 3D Printing Club. So that's all I have for you guys. Thank you guys for listening in. Yes.
If you're using the gel in the spinal disc,
Mm-hmm.
herniated disc, are you injecting gel to replace them?
Yeah, so that was the idea. A lot of, at least the gels we were looking at, there was a time dependence on how they would gel. Kind of similar to if you make Jell-O at home, you put it in the fridge and it'll set. That was kind of the working idea, was that essentially you would go in and suck all of that out, suck out all the stuff that's pressing on your spinal nerves. And then what you'd do would be like reinflating a tire. So we would take a syringe or cannula, and you would insert the gel, well, the liquid, and then it turned into gel over time. So
How would you keep the gel from going out through the herniated?
you'd cauterize it, was our thought. So you would take it, you would heat up that region, and like a wound, like you'd cauterize, like if you cut your arm, it'd be like burning it to cut it. So small, you'd burn it essentially. That was the working idea.
You're cauterizing the gel itself?
No, the annulus fibrosis that would be near it, yeah. Or, you know, probably another thing would be finding some sort of patch for that, like we would a tire. There was another option. We were really focused on more the mechanical properties of the gel itself, to make sure once it did set or it did cool and turn into the gel, that we were actually getting the mechanical properties we want. That, you know, if specifically for a spine, if you're looking at it taking any sort of compression, we wanted to make sure, you know, with it acting as a shock absorber, we wanted to make sure that we didn't have such a weak gel that it would just smash anyways, right? So that was kind of where we really focused on, was the mechanical properties and material properties of the gel. I only gave one data set there, but we did a couple different ones. The other thing you need to be concerned about is hydration too of the gels. In open air, they would dry out, but in your body, hopefully, they would stay, you know, moist. Because when the gels start drying out, we had other problems too. So.
What's the state of that research or applications today?
So there was another PhD student working on it, and he actually focused on the annulus fibrosis. So it was kind of a 2-segment one, and he did quite a bit of work after I had left the project, and that was kind of where he focused his PhD on. So his focus was more on the annulus fibrosis, and there was a couple undergraduates who worked with him. So I'm not sure if the work was ever published. We had quite a few undergraduates, so we went and presented it quite a bit, but I don't think it ever got published. So I think it's still a project. It got morphed more into the gel burn project. And I helped with that one actually a little bit more. So with the gel burn, what it was is you're putting nutrients into the gel. And with a burn, a lot of the problems they have is when you wrap a burn and put the medicine on, when you go to unwrap it, you're actually peeling off skin. And so with the gel patch, you could put that on and then wrap it. And the gel, since hydrogels are 98% water, most of them, they're going to vary a little bit, but in general, there's a lot of water there. So what it would do is it would help transport a lot of the nutrients with the medicine into it. But when you went to unwrap it, you're not peeling off the skin with that. So a lot of the knowledge that we had from just synthesizing those gels actually went into that, into synthesizing gels that would work for burn victims or ulcers on individuals as well. So to answer your question? Yes? Which one? No, that's fine. This one? Mm-hmm. Oh, so sorry. It starts empty on the inside. Thank you. Yeah, so it starts empty on the inside, and then you would push something into it. So like for plastic bottles that we use, it'd start empty, and what you'd do is you'd push it into the mold. Plastic bottles, they also, for a plastic bottle, the other thing they do is they actually blow air into it, so it'll pop it out to give it that form. It doesn't start like that. They have to push air into it. But this form right here starts empty, and then it's filled. Really the big thing I want to motivate with this thing is at the end of the day, we have 3 different approaches, but we end up with the same thing. Yeah, this one starts empty, and then you fill it. And this one's interesting too, because a lot of times, sometimes you have to apply a coating to the inside. So when you take your mold off, you don't rip part of the material off with you. So there's a lot of science and engineering that goes into that one as well. Yes? So that one, I'm going to step out of my presentation because I hit a slide because I didn't know if I should talk about it or not. But there's always that one good student, right? Give me a second. I don't know if I can, there we go. So for the chain link, that was, give it a second. So that was printed on a different type. There's a lot of different types of printers. I didn't go into that. Probably the most common one we see is the filament, and I showed the filament. HP's technology is what's called a powder bed technology. So if you imagine this is a feeder and it feeds into a bed platform. So and you can kind of see how it steps up. But what you have is you'll start with a layer, and then with this you have some sort of agent that will lay on top of it. And then you'll have an unfused region and then a fused region. And then your next layer, it just builds and builds. So this technology, you start with an initial powder layer on the build platform. That powder temperature for polymers is specifically held near the melt point. And what that is that point in a material that has crystals, those crystals are melt. It's right before that. So it's really, really warm, but not melting. We then have a print head or some way to deposit loaded droplets on it. And those loaded droplets could be, anything from like glue to hold it together, something to hold it together so we can create a solid object from that. From there, the droplets bind to the powder particles. There's a lot of different technologies, a lot of different ways, but sometimes there's an energy source that goes over, but you build up. From here is the thought process. And the powder bed is lowered, and new powder layer is spread. So as you can see, we start high, go low for the powder beds, and then our feeder is feeding over. So to answer your question, this is the technology they were using, not this exact technology, but this concept. It's very different, obviously, than the fused filament. With this, that's what they were using at HP. So if you imagine, you can put a lot of different things into what you're loading your droplets with. So they started, I think, with that was a PA12 powder. So it's a nylon 12 powder. It's used for different types of things. This probably isn't, but something similar to that, like a pretty rigid plastic. Like I said, there's other things they could have added to that, but I think it was 2 slides ago. So that's what they used. It's a different, whoops, sorry guys. It's a different type of material. This here is printed on a powder bed. This is printed on a powder bed. Some of the things that are nice about powder bed printers versus fused filament, the filaments are about 1 millimeter in length, whereas some of the powders you're using are more like on the scale of like a hair. So they're quite small, maybe a little bigger than a hair, but just to give you a difference, we're talking, if we, on the scale of 100, if that was like the fused filament, this powder is like at 0.1 or 1, so much smaller. So you can get a lot better resolution when you're looking at that. So for example, I'm trying to think of, well, they actually had pretty intricate, I don't know how well you can see this, but if you look at this, this was also printed on a powder bed, and you can see all these spikes from the wheel. The resolution to get that's pretty impressive. I think I had gears that I showed as well. To get those gears to interlock, you can get some really small resolution. Some of those are fun. You could absolutely do those on a fused filament, but some of the more high tech, if you will, some of those more engineering requirements or research and development, this gets you a lot better resolution. The other thing is with fused filament, there's some mixing you can do. If you looked at, and I should have had that picture, but there's a picture of me on this, and I have a blue, it's like a blue rigid plastic in the middle. It's a flexible material, and that is what we would start getting into is what's called metamaterials, where you can start getting really interesting material properties. With the fused filament, though, is you only have so many filaments. This, oops, a couple slides ahead, with something like this type of technology, we're showing 1 print head, but what if we have 2 or 3 print heads? We can start getting some really interesting material properties from that. So I don't know if that answers your question. I think I talked a lot, but really a different type of technology than I really talked about here. It's using powder beds versus fused filament. Any other questions?
All right, if nobody has any other questions, I just want to thank you guys all for coming. Remind you that STEAM Cafe is held on the 3rd Tuesday of every month. So next month, Dr. Jonica Morrow, who is a lecturer in our biomedical engineering department, is going to be the presenter, and her talk is called Vampires, Zombies, and Mummies, Exploring Parasites of the Past and Present. So we've continued our tradition of doing something Halloween related in the month of October. So that should be pretty interesting. If you haven't gotten pizza, please grab a slice. Again, thank you everybody for coming, either in person or virtually.
Thank you all.